All right, so first of all, we're just going to start with the basics. So what is a confidence interval? A confidence interval is a range computed using sample statistics to estimate an unknown population parameter with a stated level of confidence. So if you haven't gone over the lesson so far, you may not understand what this means, but we're going to go over a couple examples and hopefully it'll make more sense. So a sampling distribution is a distribution of sample statistics with a mean approximately equal to the mean in the original distribution and a standard deviation, which is known as a standard error. So something important to remember about sampling distributions is that the standard error is similar to the standard deviation of a sampling distribution. So just remember that. So sample size has a huge impact on your standard error. This is one relationship that you just want to remember, that they have an inverse relationship. So as your sample size goes up, your standard error will go down. And as your sample size goes down, your standard error will go up. So this also means that a larger sample size will make the distribution more normal, because as you think about it, as your sample size increases, the less variability you have in your observations. So the more normal your distribution will be, and the smaller your standard error will be as well, since there's less variability with more observations. All right, so here's an introduction to confidence intervals. Here's that definition that I just stated before. And here's the formula that you're going to get pretty familiar with regarding confidence intervals. So the formula for confidence intervals is a sample statistic plus or minus your margin of error. Your margin of error is the multiplier times the standard error. So you want to make sure that you understand the difference between just margin of error and the standard error. You don't want to get that confused, because sometimes you'll see the confidence interval formula written as sample statistic plus or minus your multiplier times your standard error, or it'll be sample statistic plus or minus your margin of error, but it's still saying the same thing. You just need to know what your margin of error is. So the margin of error depends on two factors. So it depends on the level of confidence, that is how you determine your multiplier, and the value of the standard error. So if you remember when we talked about the empirical rule before, this is what affects your multiplier, which is your level of confidence. So you typically only have 3 levels of confidence in this course. Sometimes you may have other levels of confidence, but you'll be given the multiplier for that. But from the chart that we made the empirical rule, we can identify the multipliers for the 3 given level of confidence. So if you want to be, if you have a confidence level of 68%, your multiplier would be 1. If you have a confidence level of 95, your multiplier would be 2. And if you have a confidence level of 99, your multiplier would be 3. So whichever level of confidence you have, that number that corresponds to it would be your multiplier. And then you would multiply that by your standard error in order to get your margin of error. So 95% confidence intervals are probably the most common levels of confidence that you're going to be seeing in this course. So for the form for a 95% confidence interval would be your sample statistic plus or minus 2 times your standard error. So I just want to make it clear that when I say plus or minus, you're going to be doing 2 separate calculations. So you're going to be doing, it doesn't really matter which order you do it in, but you would take your sample statistic plus 2 times your standard error, and then you would get one number. And then you would take, again, you would take your sample statistic and subtract 2 times the standard error. So those 2 numbers that you get from adding and subtracting would make the interval, which a confidence interval you're going to want to use. Oh yeah, 99%, 99.7, it's pretty much, it's the same thing. A lot of time for 95%, the actual number is 1.96, but they rounded up to 2 just to make it easier for you. But 3 should be, 3 is fine for 99, 99.7, it works. Good question. Okay, so that was pretty much all you really need to know for confidence intervals so far. But just keep in mind that the final answer for a confidence interval will be a number. You'll get two numbers, and it'll be an interval. So you'll have a smaller number and a larger number, and that will be your two answers. And you must write a conclusion statement interpreting your data. So this is really important. So your conclusion statement will look something like this. So you say, I am, for example, 95% confident or sure that the population, whichever population parameter you're using, is between, for example, 2 and 5. So that's just an example of your conclusion statement regarding a confidence interval. Okay, so now that was kind of a lot, but we're going to go over an example of confidence intervals. So at the beginning of the spring 2017 semester, a representative sample of 501 Stat 200 students were surveyed and asked if they owned a dog. The sample proportion was 0.559. There's a standard error of 0.022. We can use this information to construct a 95% confidence interval for the proportion of all Stat 200 students who own a dog. So we pull up that formula again. Confidence interval equals sample statistic plus or minus margin of error. And we're just going to plug in our numbers. So first, starting with our sample statistic, we have a sample proportion of 0.559, which goes into our sample statistic slot. We keep the plus or minus sign. Since we have a 95% confidence interval, our multiplier would then be 2. And then we multiply that times our standard error of 0.022. So once we add that, when we add so when we add our sample proportion to our multiplier, we get 0.603. And then when we subtract the margin of error from the sample statistic, we get 0.515. So we're just doing two calculations here, two separate ones because of the adding and subtracting. We just have to take turns with those. But we get an interval ranging from 0.515 to 0.603. So now we can make a concluding statement about that, and we can say, for example, I am 95% confident that the population proportion of Stat 200 students who own a dog is between 0.515 and 0.603. So then any value in that confidence interval level, so say you said 0.571, that would be a reasonable estimate for the true population value. So we're just really estimating what the actual proportion of Stat 200 students who own a dog is. And obviously we will never know the actual proportion, but we can give a range of confidence for what that actual proportion would be. All right, so moving on to bootstrapping. So we're moving away from confidence intervals now, and we're moving into bootstrapping. So bootstrapping, is a resampling procedure that uses data from one sample to generate a sampling distribution by repeatedly taking random samples from the known sample. So that's a lot of sample talk there, but it's also known as sampling with replacement. So I think the best way to understand what bootstrapping is to go through an example. So we have data concerning the heights of individuals in a random sample of 15 people. To construct a bootstrap distribution for the mean height, we would first randomly select one individual from that sample and record their height. Then, with that, we place that individual back into the sample. Then we would randomly select a second individual and record their height. So this is known as sampling with replacement because we put each case back into the sample after recording their height. So I guess the best way to think about it is probably if you had a bunch of cards and you just put them in a hat and you picked out one card and you wrote down the number that you got, and then you just put that back in the hat. So it still has another chance of being picked. So just because it gets picked once, that doesn't mean it can't get picked again. So we repeat this process until we have selected 15 values. So another important thing in bootstrapping is that you select the same number of values. So if you have a random sample of 15, your bootstrap sample would also equal 15. So we take those 15 selected values and we can compute a bootstrap sample mean. So we can repeat this process as many times as we want, but each bootstrap sample must be equal to the original sample size. So just some important things to highlight from bootstrapping is that some individuals may appear in the bootstrap sample more than once, and that's okay. That's most likely what is going to happen. And the distribution of many bootstrap sample means is known as the bootstrap distribution or the bootstrap sampling distribution. Okay, so we can construct bootstrapping confidence intervals. Two ways we can do this. So the standard deviation of the bootstrap distribution is the standard error, which we can which we can use to construct a bootstrap confidence interval. So remember when we did the 95% confidence interval, if the sampling distribution is approximately normal, the confidence interval would be equal to the sample statistic plus or minus 2 times the standard error. So that's one way to construct a bootstrap confidence interval. And the next way is if we're doing a 95% confidence interval, we can find the middle 95% of bootstrap statistics, known as the percentile method. So this is most likely preferred because it works regardless of the shape of the sampling distribution. It will work no matter what, but it may be easier just to use the formula in this case. But if you're using Stackey, either one is preferred, so it's fine. Okay, so I think I mentioned this before, but I'm just going to reiterate. You can kind of see in the visualization there the relationship again between sample size and standard error. As your sample size increases, your standard error decreases. Also, again, if your sample size decreases, the standard error would increase. So if you look at the charts on the bottom there on the left, you have a chart with a sample size of 20 compared to the one on the right with a sample size of 200. So if you look in the top right corner on the bottom there, you can see the standard error. And the standard error on the one on the left is significantly larger than the standard error on the one on the right. So you can just see how the relationship between sample size and standard error there is inverse. But also, if you remember what standard error represents, it represents the variability in an observation or a distribution. So if you have more samples in a distribution, it will be less variable since there are more observations there. Okay, so we made it through all those questions. Now we're just going to put some of those to practice. So here's the first review. In a random sample of 525 Penn State World Campus students, the mean height was 67.009 inches with a standard deviation of 4.462 inches. The standard error was computed to be 0.195. Construct a 95% confidence interval for the mean height of all Penn State World Campus students. So I'm going to give you a couple minutes, and when you get your answer, type it in the chat box, and we'll go over it soon. All right, we're going to go over this one now. So the answer here is A. We're just going to walk through it. So here's that formula again. So the top one is the most broad or the most consolidated formula, so sample statistic plus or minus margin of error. You can break that down into your sample statistic plus or minus 2 times the standard error. It's the same formula. So once we plug in our numbers, we plug in our sample statistic, which is the mean height of 67.009 inches. Then we add that to, we use 2 here as our multiplier since we're using a 95% confidence interval. And then we multiply that by times our standard error of 4.462. And then we get, so how I wrote this formula out is I calculated the margin of error first. So I multiplied 2 times 0.195 and I got 0.39. And then I just added and subtracted that to 67.009. And the answer comes out to 66.619 and 67.399. Sorry about those decimals, but all right. So if you have any questions on that, you can let me know at the end, but I'm going to move on to the next review question. This is on bootstrapping. So which of the following sets of data could result in a bootstrap sample from the given set of values? All right, so awesome. Our answer here is C. So really the 2 main factors here in answering this question is making sure that the number of values equals the number of values from the original sample. So since our n equals 10 from the given set of values, we want to make sure our bootstrap sample n equals 10 as well. So B has 8 values, I think, so that wouldn't work because our bootstrap sample needs to have 10. So A and C would still be in, but A, the second value there is 6, and I think there's a 3 in there too, and a 4. We don't have those values in the original sample, so there's no way we could get that in our bootstrap sample. So that's one of the things about these bootstrapping questions is that a lot of times the answers are obvious if you are looking for like 2 main criteria, and if they don't pass them, they're wrong. So you guys did a great job with this one. I think this is the last question we have. Based on sample size, which bootstrap distribution has a smaller standard error? Distribution A or distribution B? Okay, aside from the fact that it says the standard error on the top right corner of the distributions, which I didn't notice until now, B is the right answer because it has a larger sample size. So if you looked at the standard errors, great, but if it wasn't there, you still could have answered the question since there's an inverse relationship between standard error and sample size. So If we're looking for a smaller standard error, we want to be looking for a larger sample size.